Welcome everyone. This is the second lecture in our computer vision course. This is about edge detection. So we are still in the first block on computer vision fundamentals. We will introduce you to very simple edge detection, to the concept or the operation of convolution, which is fundamental and essential also in later lectures. And we'll discuss an algorithm called Canny's edge detection, um, for the last part in the last part of the lecture. Before we start discussing edge detection, I did not yet tell you, um, how to actually obtain positions and bounding boxes in the last lecture. While I think this is pretty simple, I still think we should let you know. So let's assume we already have found connected components, and we have obtained, let's say, this one blob here with all the pixels, set to 1 that actually belongs to one connected component. And then what we actually do is we collect all those pixel positions, so all the x and y coordinates. Let me just switch to my pointer. So all the x, y coordinates, let's think of those as vectors of n many. So in this example, 1, 2, 3, 4, 5, 6, 7 binary position or positions of those ones here. And then we just compute the average, right? So that's one way of doing that, to define the position of an object. So it's basically summing up all those pixel positions, divide them by n, so which would in this example be 7. So I did that here by hand, so we would sum up all the x values. So 1, then 3 times 2, 3 and 2 times 4, which should be 18 divided by 7 is 0.5, and the y positions is 2, 2, then 4 times 3, and 1, 4, which sums up to 20, and then divided by 7 should be 2.9, and that blue dot here, represents the center of mass of this blob. Okay, for the bounding boxes, it's fairly simple as well. I didn't prepare a slide here. You basically run or scan through this image, and because you already know the ID of your current object that you hit, you can scan through this, and whenever you hit a positive pixel, a foreground pixel, you extend your left, right, bottom, and top variables that then make up those those rectangular boundaries. Okay. So in your first exercise, you'll also find something that we haven't yet talked about, which is a concept or an operation called tracking. Tracking, let's just formally introduce you to that concept, is basically this task. Given a set of detection, and let's think of these circles here as positions in your or on your image, but you kind of have them arranged in an array, and those colors now represent identities of your objects, okay? And you have those detections for a time point t and a time point t plus 1, and now your task is to find the mapping between those objects, between those detections, such that the identity of these detections is retained. So there's no mix in colors, right? So blue goes to blue, orange goes to orange, and so on. Now, since the detection algorithm, so the one that we discussed before based on color or image brightness difference to the background, since this algorithm doesn't know about identity, it just gives you this list of detections in an unknown order. So you basically have to now use features of these detections to approximate this mapping, right? So you don't know a priori what is the identity of those objects. You can extract features, and we'll look at two maybe, and then use those properties to make an informed guess or formulate an algorithm of how to match. Now, please note that sometimes, because your detection algorithm isn't perfect, you may have missing detections. So for example, this gray detection here, this gray animal or object, wasn't found, although it was there, right? So this is a false negative. And now there's no way of connecting this guy to the next frame because, well, that's basically a new detection. Yeah. Having said that, the tracking problem can be formulated over more of, more time steps than just two. But another thing to mention and to note here is that also, in that source frame at time t, we may have new detections or even false detections, and it's really now up to you how to formulate this tracking solution to not connect this guy to real detections, to true positive detections. No? Okay, and so in this lecture we won't be going much into detail, about tracking. I'll share with you a link to a paper that we published in which we use machine learning to learn those correspondences. But that's about it in the tracking. In the exercises, we will look at one tracking problem or one tracking solution for a given problem. And that's the simple tracking algorithm. And let's have a look why I think that's the simplest tracking algorithm. So first, let's think of two objects given, and we already know that detections belong together here, and now at time t, which probably is this position for the yellow object and this position for the blue object, we have two possible candidates. And the question now is, okay, do we connect this blue detection with this candidate or with that? And do we connect this yellow candidate with this, this yellow detection with this candidate or with that one? And obviously, you probably have, an idea and would, I guess, connect this candidate with this detection here and that one with this one. But how do we actually determine this? So what kind of property can we use to connect these properly? And so the simplest algorithm here is this one. So we first get all the candidates for a given time point, which would be these two, and we call this set C. And then we iterate over all the last detections in our set D of detections. So this would be these positions of yellow and blue. And then we just look at what the closest candidate is to D, right? So, and then this obviously goes back or relies on a definition of what close means. But let's think, for now as just the Euclidean distance, okay? So, so given, the blue detection here being our D or D here, the closest detection or the closest candidate would be this guy. So we would add in our set of, or in our mapping between detections, this pair D and C, and then we'll remove C from our set of candidates because it is already you know, it's already linked to one of those detections, so it's not free anymore to be linked. And then we'll continue. So the remaining detection in our set D would be the yellow one, and then the only candidate left would be this one. And then you would find the proper mapping. Now, apparently, it's not a perfect algorithm. It's just the simplest, idea of a tracking algorithm. So my question for you now is, when would this fail? So under which conditions would the blue detection here be connected to this apparently wrong candidate, and the yellow detection here connected to this candidate here? To give you a hint, so is the result or the result set invariant to the order of our last detection? So if we would iterate over the set capital D, what happens when we change the order? And also, will those problems become relevant when we are tracking only a single object? So those two questions, please think about them, and I'll ask them in the Q&A session. Now, what can we do to improve, the results? And one of those things that we can do is we'll just change the recording frame rate. We increase the recording frame rate. So whatever motion there is will be translated in only little image movements, right? Or image motion. So the actual object appears much closer to the old, the candidate, the actual candidate appears much closer to the old position. And you'll find an example video in your assignments in exercise 1.3. We have taken this high-speed video here, so the object in motion is really not far away from the previous position, but still you can see here that it may be split up in two bounding boxes, and then you kind of know what your answer should be to one of those previous questions. What kind of problems you may face, even if there's only one object to be tracked. Okay, now let's move to today's topic, edges. And why are edges important? Well, because they make us see things, right? So, for example, let me use this joke by a German comedian called Otto. He's probably like 100 years old or so, but it's still funny. The white eagle on white background, right? So you basically don't see it because there's no edges, and edges are very robust features. Edges have been used in the past as one of the main features that people would look for, that features that define an object's shape or the existence of an object. So why would people resort to just the edges? Well, because they're pretty stable. So if we have global changes in brightness, for example, like over day and night, over the course of day and night, you would see patterns, local image patterns, get brighter overall, but still this local contrast, this local change in brightness, whether it's from dark to light or vice versa, would still be retained. And so what an edge image is now, we look for these structures and then binarize them. So we say 1 if there's an edge and 0 if there's no edge. And this way, right, our image brightness changes are, binarized now, and it doesn't really matter whether they are, you know, in the original image in a very bright part of our values or in the dark part of the values. You still have the edge, and we will binarize them. Okay. Now, why is this important? Well, or when would this be applied? Here, for example, it's just one of those hundreds of millions examples where you can use these and where this has been used. For example, when detecting the, the lane borders or the middle lane here, and that's a paper which is already 7 years old, but still very in a very actual and let's say modern context of self-driving cars. Okay, let's have a look at different properties that we need to be aware of when we look for edges, because those variations need to be handled in the way we detect edges. Okay, so the first property, let's say, is the steepness, let's say, of an edge of the image brightness. So look at this image here. We have a gradient from black to white, so from dark to light. And if we just extract one row of this image and look at the brightness over this position X, we see that there's like a plateau of black, and then it gradually becomes lighter, and then there's a plateau of white. But the slope with which this change appears is pretty high compared to this other example here, where we do have those two plateaus here and there, but the gradual change is much slower, so there's much more image space, let's say, over which this change occurs. Now, this gradient or this edge could also be rotated, right? So that we would not detect any change in image brightness looking, over the X direction. But we do find this if we take an image column. Yeah? So if we look vertically over this image, we see the same pattern. Now, how can we extract that information? And the first idea that hopefully comes to your mind is using the image derivative. And so what is this? Well, we basically look at two positions in the image, x and x plus some delta, and we can think of this as being 1 pixel. So we look at the image, or we compare the image brightness between two neighboring image positions. And well, that's basically our derivative, right? So here in this example, we look at the image brightness at position x plus 1 and x, which is the yellow position here, or the yellow brightness here. And then we subtract these, and then we get a positive value, and 0 otherwise. Yeah. Now, if we do that again for that gradual change here, this results in a much lower peak, let's say, but a much broader edge, let's say. Okay. So how would we then detect the edge? Well, there are always different options, but the most simple option would be to look at a threshold. So once our image derivative is above a certain threshold, we would then mark that position with a 1, otherwise 0. And you can now see what the challenge here is with this gradual change. So if we still want to detect this as an edge, we would have to finely tune that threshold, and there's no apparent way, or no no clear path towards an automatic, let's say, automatically determined threshold. So the zero and the peak here are pretty far, pretty close, and that also gives us a notion of how robust that may be with respect to outliers or to noise. Okay. Okay. But by the way, edges would probably be, or probably have to be, um, you know, higher in slope, right? For us to think that's an edge. Okay, so you can detect edges by comparing neighboring pixel brightnesses, but let me tell you, nobody does that anymore. We use convolution. And convolution is a very important, very fundamental, operation also in signal processing. So you should be aware of what convolution is. Think of convolution in the 2D discrete, image scenario as the following operation. So we have an underlying image and a so-called kernel. So those two are basically images, and the kernel oftentimes is smaller. So here it's a 3x3 matrix, and we shift this kernel over the image, sequentially, and at each position, the entries in the kernel are multiplied by the pixel brightnesses that correspond to that specific position that it has, and then all those weighted pixel brightnesses are then summed up, and the result has been written then in the output image. Okay, so this is the first notion. We have a weighted sum of pixel brightnesses, and the weights are expressed as kernel coefficients. Now this is the equation. So we have our image and we have our kernel k, and we iterate over all the indices. Think of w and h as indices that are centric. So the middle position here is 0, 0, and then the kernel is centered on an image position xy, and so the output here is just a scalar value. The operation usually, or is usually represented with, or notated with, noted with this sign, with this asterisk. But what we actually do is basically have two vectors. So the vector of pixel brightnesses I, right? So if you just pull this into one dimension, and k, and then you have this dot product, which leads me to tell you what my favorite notion here is, which is basically like a pattern kind of matching, right? So a pattern that is defined in k and a pattern that is defined in I are matched so that the value is large when those patterns are similar, or are large but negative when they are um, exactly the opposite, and if they are orthogonal, so if they do not correlate at all, then the dot product is 0. Okay, so I would like you to think of convolution as something that's very similar to correlation, and also if you look up the equation, you will only see slight differences in how it's defined, and but the underlying theory behind it is something that needs to be taught in signal processing or more theoretical courses. Okay. Now, convolution then can be used, as I said, for various tasks. For example, if we use a kernel that has a constant, um, uh, like throughout its dimensions, so let's say 1, 1, 1, 1, and we basically do a sum of all pixel brightnesses in a certain region, right? And that region is defined by the size of the kernel. Now, there's something missing here. maybe one of those questions in the Q&A session would be, okay, what is missing here? And yes, we can also detect edges with convolution. So what would this kernel have to look like if we had to implement the very simple, compare neighboring pixel values kind of solution? So what would this kernel have to look like? Okay, so I don't give you the answer here. There's two entries in K, and you could have them this way or that way. That doesn't really matter. You can also transpose the K, so you look for not vertical edges but horizontal edges. But let me show you another kernel that can be used for edge detection. And so this is basically comparing not the direct image neighbors, but it compares that pixel and the next to the direct neighbor, right? And also we have not just then 3 entries but 9, because for the vertical direction we kind of smooth or take the average of neighboring pixels. So right, so 1 1 1 means we sum these neighbors up, but then we give them a negative sign because we want to compare these, right? And this can be then applied to an input image and results in an image that now ranges not only between 0 and 255, but may have negative values, right? So, for example, look at this corner, or this edge here. This is an image brightness change from dark to white. So this is a negative edge, although edges, remember, are binary, so this is not yet binarized. And then, this more or less vertical contour here of the dog is very well highlighted. Now, if we then, rotate or like flip the kernel by taking the transpose, we can then detect edges that are horizontal, right? So with a flipped kernel, we take the image derivative along the y dimension, and with the original kernel, we took it along the x dimension. Okay?
So another famous detector, edge detector, is the so-called Sobel kernel. It's also 3 by 3. It comes in 2 versions, one for taking the image derivative in the x direction. That's why we call it SX. And one for taking the image derivative in the vertical direction, SY. And so what we'll do is we convolve the image with SX to obtain a matrix called GX. And we do the same with SY, and we'll obtain a matrix called GY. Now, what we do with that, and the reason why we call this G, is described on this slide. So here we define a property that we call the image gradient, which is basically a vector of the partial image derivatives. So nabla I at an image location x and y is defined as a vector of 2 components. One is how much the image brightness change when I change x, and how much the image change along the y direction. Delta I over dx and di over dy. Of course, this is a vector field, so we obtain different contents, potentially different contents at every image location. So you can think of this as your image brightness landscape again, and we'll look at x and y and compute the gradient in both directions, and the steeper this change now is, the larger those quantities, obviously. And so nicely you can think of the gradient as a vector that points into the direction where this landscape has its maximum slope. Yeah, and that always tells you also, because that's how we define an edge, the edge's direction as well, because that's orthogonal to the gradient direction. Okay, so the gradient vector is basically a 2D quantity, so you often find this to be attached to this landscape in a way, pointing upwards. But basically what it is, it just points in the 2D image plane into the direction where this landscape, this brightness landscape, and any other function, has its maximum slope. Now we want to do this on images. So think of an edge from dark to white, for example, here at this point. So again, this is just a definition that I copied here. So the image gradient at this xy position is the vector of its change, of its brightness change along the x direction and along the y direction. So at this point, what would this vector look like? So do we have something non-negative here, and is it positive or negative? And do we have something, something non-zero here, and is it positive or negative? And do we have something non-zero here, and is it positive or negative? So obviously, there's no brightness change along the y direction. That's why this is a 0 here. And then we don't really know what those actual values were, but there's a positive change, right? So from something dark to something bright, it should be positive. So this, could be a 1, could be a 20. We don't know. And then if we rotate the image or rotate the edge, we see that now, what happens to the x and to the y partial image derivatives? What do you think? What's going on? Okay, and we'll clear this up later in the Q&A session. Just for now, to summarize what we just learned here, we can use the gx and gy, so the results of the Sobel filter convolutions at their respective positions as an estimate, as an approximation of the image gradient at this position. Now look at this example again, at the dog with its tongue out. Here, this image point, this image location at the nose has negative values for the x gradient. So that means that the gradient, points backwards. And also a positive gradient at that, or partial derivative for the y direction at this point. So that means that for that point, the gradient vector points downwards and leftwards, but that's the gradient direction. Now, let's come to Canny's edge detector. We already have all the components in place. This paper is one of those papers that you really want to have in your career. Has been cited heavily. Even now, I think the citation numbers are increasing, so I don't even know if that is still accurate here. Please look that paper up. It has been published probably around the time you were born, or even before that. So it's one of those things that you have to know. Okay, let's first define what we think should be a property of a good edge detector. First of all, obviously, we want edges to be detected as edges and no edges to not be detected as edges, right? So we would like to have a low false positive rate and also a low false negative rate. Obviously, that's what we want in any binary classification task. Also, the edge point should be accurately localized. So we don't want an edge that is here to be detected here or there. But that's pretty clear. Whatever task we want to run on that edge detection task, we want that task also to be solved accurately, right? So lane detection or whatever you want to detect shouldn't have a systematic or some other offset. And also, and that's nothing uncommon, or nothing that was uncommon in the past, some edge detectors would produce double edges. And oftentimes these were not just double, they're also conflicted with requirement number 2, and that's why we specifically don't want that. I think we'll discuss that in the assignments, what kind of edge detection will produce double edges. But so far, those 3 requirements set out in the paper as the standard requirements. And let's see how Canny solved that. So Canny's edge detection can be summarized in, I think, 5 or 6 steps or so. First, we'll smooth the image. That's necessary because some images are noisy because the sensor is overheated and then produces some kind of erroneous measurements. And oftentimes in real world data you can't do anything about noise, so what you can then do is get rid of small small pixel noise by smoothing the image. You already have seen one kernel, the constant kernel, that you can use to smooth the image. We'll use a Gaussian kernel, and I'll explain that in the next slide. We'll then compute the image gradient using the Sobel filter, as we have seen, and then apply a non-maximum suppression. So whatever we think is an edge doesn't need to be described by many more pixels than the minimum set, and we'll see how we do that. We'll use 2 thresholds for defining strong edges and also weak edges, because we want edges to be contiguous, even through regions where the edge isn't as strong as in others. We call that process hysteresis. We'll track edges along their edge direction and suppress all those edges that are weak unless they're connected to strong edges. And we'll look at that exact process on the next slides. Okay, let's go. First, let's use a Gaussian kernel to smooth an image from a crisp-looking, sharp image that, if you zoom in, may have a lot of grainy kind of artifacts, and these will show up in the image gradient. And we don't want that, so we'll use a kernel that looks like that. And so you see that in the center, coefficient is the highest. So going to the periphery of the kernel, the image pixels are weighted less and less, and the way this function falls off is a 2D Gaussian. So you could look up the function on Wikipedia, and then you'll round those values, and then you come up with this kernel. But why do we want to divide by something that I don't tell you? That's a question for you in the Q&A. So just imagine you sum up all those weighted pixels with a weight larger than 1. So what kind of image will you get? And also, what happens if your allowed image depth is only 8 bits? And then, so what then would you have to divide this kernel with? Yeah. Okay, let's go. Oh, and by the way, how do we treat color images, right? So how can we convolve this matrix with this kernel? Also a question for the Q&A session. It's simple. Don't worry. All right, let's go. The image gradient is a vector property. And we'll soon, on the next slide, look at strong and weak edges. So we need to define what strong and weak means. So we already looked at how we can produce gx and gy. Now let's define the gradient magnitude, capital G, as the length of the gradient vector. So that basically is the pixel-wise square sum square root of that. And so we have a matrix that has the size of the image, and which has the length of this gradient vector stored in each of these image locations. Now we'll use then the angle of the gradient vector, which is a two-dimensional property, but we actually just need an angle. We can extract that angle by using a tan 2, which provides an angle between 0 and 2 pi. And that also is a matrix. We'll then use, we'll then round theta to 8 discrete directions, which correspond to 0, 45 degrees, 90 degrees, 135, and so on, to represent the 8 different neighbors that we have in the already presented 8 neighborhood. Okay, so the first step here is now to create edges that are thin, that are exactly on the edge, and not ones that are off the edge. Look at this image here. We have a thick line, and if we look at one cross section of this may look like that. If we binarize that, use the threshold like this dotted line here, we would obtain a pretty thick edge with many pixels in width. And our task now is to thinnen this, right? So to just have 1 pixel remain, because that's enough to describe the edge. And remember our first 2 requirements. We want no false positives, and we want it to be accurately localized. Okay, so how do we do that? Look at this image location here, the yellow circle. The way we want to thin out that edge is by looking along the image gradient direction, and to remove non-maximum pixels or non-maximum edges. So scan over all pixels, compare the edge magnitude, remember that matrix G, with that of its neighbors, and we'll only use those neighbors along the image gradient direction. Neighbors then are discretized into 8 different neighbors, so we'll just have to observe 2, right? So 1 in this direction and 1 in this direction. And we'll suppress this pixel if it is not greater than any of those. Simple as that. So, question. Look at this 3 by 3 matrix and look at the center pixel. For which gradient direction would this pixel remain, so not be suppressed? Okay, let's discuss that in the QA session and move on. We'll now introduce 2 thresholds. One that I'll call here theta h for high, theta l for low. And obviously they define gradient magnitudes that strong edges exhibit. So any gradient magnitude above this threshold is a strong edge, and gradient magnitudes above the second threshold are still edges, but they're weak edges. So think of an edge to have that kind of gradient magnitude. We have two pieces that are strong edges, and then one piece of the edge which is meh, could be. And our goal is now to remove all the weak edges. So for example, this part and the one that is covered by my video here, but not this part because it is connected to strong edges. Okay, let's go. So you'll be looking at how to do this with Manuel in the exercises, but it's not that hard, and you can read that paper anyway and re-implement what you read there. I have run that algorithm for a couple of settings. So sigma is the standard deviation of the Gaussian kernel. So we'll have a look at what kind of effects that introduces. But look at L. So theta L and theta H now are chosen differently. So for high values, so for non-different values, you'll see that still. So that's basically saying all the strong edges defined by that one threshold are taken as an edge. And you see, compared to an image that has an even stronger threshold, it looks much cleaner. Yeah? So many parts here just don't show up anymore, and the outline of the dog and the tongue are well preserved. An even better result, I think, judging subjectively, is shown here, where we have a low threshold, like a low threshold at 0.2, and the same high threshold as up there. And now we even see those structures here and the buildings be retained, and also the tongue is much closed already, and also this head, how do you call that, flower, looks well. Okay, and then obviously you can have much worse configurations. The thing is, you have to find those yourself. There's no way we can tell you what are optimal values for a given image. That's what you have to obtain empirically. Now, the smoothing factor plays a very important role. So we use, for example, here sigma equals 1, and that means the smoothing is not as strong. Also, small edges, small image structures will be detected as edges. And if you have larger sigmas, so stronger smoothing, those small image detail will be, washed away, and then you basically only obtain those strong edges with, let's say a larger scale. Okay. Okay, so that was edge detection and Canny. I hope you enjoyed that. I hope the audio quality was sufficient for you to understand. We will ask a couple of questions that weren't cleared up here in the video. I think that's on Wednesday, so the day after tomorrow. I hope you collect a couple more questions. Well, that was me. Enjoy. See you next time.